Hello, guys. Nice to see that you are back, Chiara. Yes, so several announcements, guys. I appreciate that you haven't asked me too much about the exams, as is usually done by calculus students. Your exams, I presume, will be delivered back to you on Monday, together with a new surprise that I am working on, right? And that will also be available Monday. I will send that surprise Sunday night or Monday morning, and it will be very clear to me if you opened the surprise and looked at it. Yes? By the time the class begins. Good? Any questions? So expect something to arrive on Monday, both somethings. One of them is your exam. Yes, of course. Once I send it, it will be like a Kinder surprise, right? On Monday morning or Sunday evening. It is so exciting. I could not sleep until 5 o'clock today, right? Preparing that surprise for you. And I'm still not fully satisfied. That's why it will be delivered just later. Good. Our time is drawing to an end. Of course, what should we do? Is it positive? Well, that depends on what is positive for you, right? It is very positive for me, or maybe it's very negative for me too. I don't know. I mean, it's not quite clear. And it will, of course, be sent through email. Yes, but don't worry, right? There is no way you will miss it. So, and of course, since our time is drawing to an end, I think after class, perhaps we will play one round of what, when, where. There are 3 questions that I want to present through the class, if you are interested in, that you have a chance to answer, right? That are pretty interesting, I think. One of them is easy. Today we'll do the easy one. The others are very hard, but you absolutely have the chance to answer it. I mean, maybe. So back to the lesson, guys. I hope more of you are able to join. No, I was wrong. No, not more of you are joining. Just 13 individuals. How horrible is this? How terrible. Well, it will make me vindicated on Monday. All right, so back to this topic, guys. Here is what we began covering. This chapter for random variables is about to be over. We talk about Chebyshev inequality. Remember, just a quick recap of what happened last class. We showed that you can use the expected value of a random variable to estimate probability. So expected value and variance are also useful tools in estimating probabilities, at least in theory. So Markov's inequality tells us that if x is bigger than or equal to 0, if it's a non-negative random variable, then the probability that x is bigger than or equal to some value alpha is less than or equal to the expected value of the variable divided by alpha. And why was that the case? Here is a simple calculation that verifies it. So alpha times probability x bigger than or equal to alpha is the same as alpha multiplied by the sum of probabilities for all the x that are bigger than alpha, right? You see that? So it's the sum of probabilities for all x bigger than alpha. And instead of multiplying those probabilities by alpha, I will make a larger sum if I multiply by the x's. Agreed? You can see that's why it's set up like this, right? So instead of I can just multiply it by alpha, but instead if I multiply it by x, I make the sum larger. That's clear, because each xk is at least as big as alpha. And because that's where the last part is where we use the fact that it's non-negative, is that we can complete and make it look like expected value. Do you see the summation looks like expected value, but it's missing the x's that contribute values smaller than alpha, right? So if I add them multiplied by the probabilities, I only make the sum bigger. That makes sense. Yes? So that would be the expected value. So you can see expected value is bigger than this quantity, and so dividing the expected value by alpha will give us an estimate of this probability. And then quickly, Chebyshev's inequality is what we need from Markov's, right? Chebyshev's inequality tells us for just a normal random variable x, not normal, I should say, just a random variable x. Normal has another meaning here. With mean mu and variance sigma squared, we can estimate the probability that the distance of x to mu is bigger than or equal to k. This probability is always less than or equal to the variance divided by k squared. And the proof is by Markov's inequality. Do you see absolute value of x minus mu bigger than or equal to k? So absolute value of x minus mu makes it a positive random variable. Yes? And the reason I square, guys, there is no reason to square anything. The reason I square is that when I have x minus mu squared, that's just the variance. The expected value of x minus mu squared is the variance. So I square this and I square the other part. We have this expression. Yes. And now I can apply Markov's inequality. This would be less than or equal to the expected value of x minus mu squared divided by this number, k squared. The numerator is just sigma squared. Yes. And here we solved this question. Let's just quickly review that question just to be sure we are all on the same spot, especially that in my notes there is a mistake. And I hope you noticed that mistake. So suppose that we have a bakery, and the bakery bakes a bunch of cakes, and the average per day is about 50 cakes. Good. Now, what can you say? You see, you have no idea how this is distributed. Maybe the bakery makes consistently 50 cakes every day. Maybe it's just some distribution. We have no idea. But let's say by looking at the records of this bakery, we see that the average is 50 per day. What can be said about the probability that today 75 or more cakes will be produced? Yes. So then I want to know what's the probability that x is bigger than or equal to 75. By Markov's inequality, because the number of cakes I produce is positive, right? It's not bulimic cakes. There's no negative sense of a cake here. So it's either 0, 1, 2, 3, right? So it's a positive random variable. And I know the average, the expected value is the same as average. The average is 50. So the probability for sure has to be less than 50 divided by 75. So the probability that more than 75 cakes or 75 or more cakes will be made is less than or equal to 50 over 75, which is 2/3. Yes, it could be much less. I do not know. Maybe the probability is 0, right? Maybe consistently you make 50 cakes, but it cannot exceed 2/3. That's what I know about it. It's an upper bound estimate. Good. Now, suppose I have further information that I know the variance is equal to 25. I want to estimate the probability that between 40 and 60 cakes will be produced today. Yes? How do I do that? Well, I begin as follows. So I know I want x between 40 and 60. Then I say x minus 50 is between minus 10 and 10. Yes? And that means that absolute value of x minus 50 is less than 10. So this probability is the same as absolute value of x minus 50 is less than 10. And then afterwards, the last part of this is incorrect. That's what be careful, guys. That is incorrect, right? Because I need absolute value of x minus 50 bigger than 10. That's when I can use Chebyshev's inequality, yes? So what do I want from here? So from here, this probability, let's correct it here. This is the same as the probability that x minus 50 squared is less than 10 squared. You agree? And this probability is the same as 1 minus the probability absolute value x minus 50 squared bigger than or equal to 10 squared. Yes. Now this one I can estimate. This one I know that the number I'm subtracting is at most 1. So this number that I'm subtracting, so it's like 1. The biggest number, basically the biggest number I subtract, the smaller is the probability. Yes. So this probability is bigger than or equal, not less than or equal, but bigger than or equal to 1 minus what? The estimate, the biggest thing it can be is the variance. The variance we know is 25 divided by this number, by 10 squared. So which is now equal to 1 minus 1/4, which is 3/4. Yes, which means that it's more than 3/4 likely that this amount will be produced. That the actual number of cakes produced today will fall between 40 and 60. Not 1/4, not less than 1/4, as I said over here. So make sure that you understand that I made a mistake. Good? Everyone's clear on it? Oh, I see 3 more people joined. That's nice. Yes. So now we talk about a very interesting topic, I think, weak law of large numbers. Now, what is this saying? Remember, we began this class by using this frequentist interpretation. We just imagine, well, if you perform something repeatedly, nature will reveal its preference, and that will be the probability. Yes. So if you apply the axiomatic approach, I think the axiomatic approach that we refer to, I think it's due to Kolmogorov, a Russian mathematician, if I'm not mistaken, that he axiomatized it, right? If you apply the axioms of probability, in other words, you interpret probability to just be a function that carries subsets of a sample space to numbers between 0 and 1 with the appropriate properties, then it behaves like this frequentist interpretation. It implies the frequentist interpretation. Yes. So what it means is this. So suppose, guys, we are going to have we have a sequence of independent and identically distributed random variables having each the same mean mu. Right, that means that we perform an experiment. So the random variables might be indicator random variables to tell us whether the coin came up heads or tails or something like that, right? So right, it's usually, yes, that type of thing. It could be anything else. So then the estimated average is just the outcome on the axis divided by n. Do you agree? That's the estimated average. And if n is long enough, that means if we actually conducted experiment with enough trials where n is big enough number, then the probability there is a difference from the theoretical average is going to decrease to 0. Does the statement make sense? It's just that same statement we did in the table when we introduced chapter 2, I think, right? Or chapter 4, when we began calculating expected value. Remember that the way we did it with the wheel, we constructed this table and we were looking down the row of this table, now the rows of the table, and seeing what the average converges to. So this is saying that the convergence will you will see that if you take a sample of a big enough size n, the difference between the theoretical average is going to be very negligible most of the time. You see, it's going to be very unusual to see a major difference from the estimated average. Like, remember, we rotated the wheel millions of times, I think, something like that, right? So we span the wheel millions of times. We did the similar things we did with the coin tossing and whatnot, right? We did it many times. So this will go to 0. Now, why is that the case? Well, how am I going to estimate this probability? You can see it already. It looks very much like Chebyshev's inequality. So first of all, I need to figure out what's the average of this thing, right? What's the average here? The expected value is, because they're independent, it's just, well, it doesn't even matter if it's independent or not. Just by linearity, it's 1 over n, the expected value of each of them. So it's going to be mu, right? The expected value of this thing is mu. You're all with me, guys? And I'm hoping it's not, it's difficult enough, so it's easy to be convinced, to be confused. So you see this, right? So this is mu. Now, what is the variance? So because they're independent, we know covariance is 0 and variance is in fact additive. So I can just first factor 1 over n. When I factor 1 over n out of variance, it becomes 1 over n squared. I hope you remember why, right? Because variance is this minus the average squared. So when you factor 1 over n, it will square it. Okay, so we have, and then the variance of the sum is the sum of the variances. Now, what's the variance of each of them? The variance of each of them is the same, so it's sigma squared, and we have n of them. So 1 over n squared times n times sigma squared becomes sigma squared over n. So you can see that variance will be decreasing, right? So this average is kind of squeezed closer and closer around mu. Right, so, and then what do we have? By Chebyshev's inequality, the probability that this expression minus mu is bigger than epsilon is less than or equal to you see this variable, to the variance of x1 all the way plus xn divided by n of this variable divided by n. That's it, that's here, right? The variance, and the variance I need to divide by the square of this number, by epsilon squared. Yes, let's see a concrete example, which hopefully will help you see how this is useful. And again, guys, stop me at some point if something is unclear. So this calculation tells you, it's very useful because it will tell you, let's say, how many times must you perform an experiment to see that result that you believe theoretically should be visible, right? So how quickly is the convergence going to happen, right? Let's say, how many times do you toss a fair coin before you are convinced that the probability is 1/2, right? That the convergent number is 1/2. Okay, so this is what we can do, that we can apply it for. So here is exactly what we are going to even do, right? So let's take a fair coin, and we want to know how many times do we toss it, so that that the probability that the sample average, you know, is going to be that how many times did we get tails over total, right? So that I want the sample average, that's the frequentist interpretation. I want it close to 1/2, right? What's the probability that the sample average is going to be, how large must the number of trials be for the sample average to be deviant by no more than 0.1 from 1/2, 99% of the time you perform this experiment. You understand? Every time you perform this trial, even if it's with the same number of coins, you will get a different sample average. And sometimes it could potentially be very, very far away from this theoretical average, right? The theoretical average is what you expect to see. That's what we understand probability how. We take this coin, we toss it many times, and the ratio of tails divided by total approaches 1/2. Do you agree, if the coin is fair? Because that's what we imagine nature does for us, right? Now, suppose we performed it n times, the experiment, right? So it is very possible, I mean, maybe not very, but it's possible for any n that all of them came to be tails, and then it will be very, very deviant from 1/2. The average will be then 1, very deviant from 1/2, right? But I want it, in some sense, it's a bit meta. I want it to be very, very unlikely, right? So basically 99% of my experiments, I want them to be not deviant by more than 1 decimal point from 1/2. And I want to know how many such trials I must perform. So what do? I define a sequence of indicator variables where xk is going to be 1 if the k of toss is tail and 0 otherwise. Yes, and clearly the expected value of xk is 1/2. right? So, and then clearly the variance is the expected value k squared minus the square of the expected value, which is 1/2 minus 1/2 squared. You all see why it's 1/2 still, right? It's just 1 squared multiplied by probability of getting tails minus the expected value of tails, right? Which is, we calculated it to be 1/2. So it ends up being what? 1/4, right? So this is what we want by the law of weak numbers. By the weak law of large numbers, we want the average minus 1/2, the probability that it's more than 1/10 in absolute value. I want it to be less than 1/100, because 99% of the time means 1% of the time it happens to be, 1% of the time or less, this border is breached. The difference is more than 1/10 of a unit. Make sense? Stop me, guys, if at some point I miss you. I failed to communicate it, as it is pretty interesting and rather important. So what do we have here? So by applying Chebyshev to this expression, we know well, by applying the previous estimates, whatever it was Chebyshev or whatever the theorem we proved, we already proved this thing, right? So it is what? It is the expected value of this thing. The expected, so the variance of this entire thing, the variance of this entire thing is 1/4 divided by n, because we have n variances, right? So each of them has variance 1/4, but because it's divided by n, I can factor it, it's 1/n squared. Variance of each of them separately can be added because they are independent. So variance of the sum is sum of the variances. And what do we get? We will get that the variance of this variable, of the average variable, it's just the variance of a single one of them divided by n. Yes? You all just verify that. You understand why we did it? We did it here. Right? Here is the general calculation. Right? We factor out 1/n squared. Then the variance of the sum is the sum of the variances, which are identical. So each of them is sigma squared. So it's n sigma squared 1/n squared. So when I simplify it, sigma squared over n. So that means that if I know the variance of x1, the variance of the average is the variance of x1 divided by n, which is 1/4 over n. And then I also need to divide by this number squared. So it's 1/4 over 1/10 squared n. And if I simplify it, I just it's 25 over n. And this number has to be, n must be big enough for this to be less than 1/100, which makes what? Which makes n bigger than or equal to 2,500, which means that you would like to toss this coin 2,500 times. And if you do that, if you conduct trials where each experiment is consisting of 2,500 tosses of the coin, 99% of the time, the average you will obtain will not deviate by more than 0.1. Right, so it will be something like between 0.49 and 0.51. That's what it tells me. You see, if I perform this experiment, you can just run simulations. Does it make sense, guys? If I perform this experiment of tossing a coin, if I just take a coin, physical coin, or simulate it with a computer, if I perform this experiment 2,500 times, one experiment is 2,500 times. And I perform this experiment involving 2,500 tosses of the coin 100 times. 99 of those times I perform it, the result I get is between 0.49 and 0.51. And one of those I might still get something different. Clear? So it gives me a sense of how frequently my experiments will agree. If I use this number of trials, my experiments will agree 99% of the time. Okay, 1/100, where it came from, that's just that's arbitrary. I just decided to create some sort of you are never going to get exactly 1/2. If you perform the experiment, you will never get 1/2 precisely. It's going to be different from 1/2. right? When are you going to consider it 1/2? So I said, let me decide that I believe it's 1/2 whenever it's different from 1/2 by no more than a 1/10 of a unit, right? If you could do more, if you it might not look to you like 1/2. Maybe you want it to be different by less than that, right? Maybe by 100th of a unit, right? So that's where I pick this thing up, right? I pick this. This is my that's my resolution of 1/2. That's how good I believe something is 1/2 or not. It's like delta epsilon type of argument, right? What is 1/2? You don't really see 1/2 precisely. You see an interval segment that is, if it's small enough, it looks to you like 1/2. So I decided to have a pretty poor resolution and decided 0.49 is 1/2, and anything in between 0.49 and 0.51 looks to me like 1/2, and everything outside of that interval does not, right? So why is it 1/100 squared? That's because I take this number that I decide here and I square it. So you can see that that the number of trials to perform to get an extra digit is going to be much bigger. You see that? Because imagine I wanted to replace this and I want to require no more than by 100. That's same thing 99% of the time, but no more than by 100, right? So that would be the 99% of the time. That will give me this 1/100. But here this would be 1/100 squared, and you would have to toss many more times. Yes. Very nice. So now let's try to say a few things about strong law of large numbers. If you want to, we can prove it. If not, we might skip the proof. It's up to you. But I will at least state what it is doing and try to compare them. So strong law of large numbers is, again, picking the sequence of independent and identically distributed random variables and taking the ratio over n and taking the limit, and the limit equals mu with probability 1, right? So the strong law of large numbers is not looking at the estimates. What it's doing, it's just saying that the sequence that is indeterminate. You see, I mean, if I perform like the previous experiment, right? If I perform 100 experiments where I try to estimate 1/2 using 2,500 trials, most of the trials, like 99 of them, will give me an estimate between 0.49 and 0.51, but one of them will deviate. Right? And if I increase the number of trials, I mean, the deviation will be less frequent, but I will still have some experiments that disagree. Right? You have some sequences that the conclusion is, well, it's not 1/2. Right? You just if you do perform enough of them, there will be some of them that are even very, very far away from 1/2. Right? So even if you perform 2,500 trials, I mean, in theory, if you really perform it so many times, there would be one situation where all the trials resulted in tails. It's going to be tremendously unlikely, extremely unlikely, but it's at least theoretically possible, right? So there could be major deviations. What this is saying is that if you make it an infinite sequence, you will always see that the result is the same. The result is the theoretical average. It's never deviating. So the sequences are different, but they converge necessarily to the same value, right? So before I decide whether to prove it or not, for you, you see the proof is not so simple, not like before, right? You can see a little bit more calculations and more explanations involved. But just quickly, let's just try to see before we talk about it how they are different, right? So the difference is for instance, you can see there is a sense of weak convergence and strong convergence, which you learn in analysis. So what you have is here is an example of a strong convergence, you see? AN is a strong convergence. You can see that the sequence AN goes to 0, right? Now, what do you observe? I mean, if you look at the rows of this, you can imagine this is a table. You look at first row, second row, third row, starting from some row going downwards, it all looks to you like 0, right? So if you remember proofs of epsilon and delta, what is this really? It's about communicating. Chiara, you remember, right? All right. I just wondered. You looked with such pain. I think was it a very painful memory? Delta epsilon. I can explain it to you where it would not feel painful. I think maybe I'm wrong, but the idea is very simple. What's delta epsilon trying to do, guys? It's just imagine you have a detector, a machine, right? And it's looking at each entry in this row, and it's trying to say 0 or not 0 in this particular case. Is it 0 or not? Now, what looks to you like 0, right? I mean, eventually, if something is very small, you can't see it. You say 0, nothing detected, right? If the quantity is too small, a detector cannot measure it. It will say it's 0, even though it's not true necessarily. It might still not be 0, not an actual 0, right? Something might be there, but it's so minuscule, but it cannot be detected. That's true of any system, right? It's true of your eyesight. It's true of anything, right? So what is epsilon? Epsilon is the ability of the machine to detect a difference. That's the border beyond which the machine is not able to detect, right? If there is a deviation of the number from the target by less than epsilon, the machine cannot detect the difference. It would say there is no difference. Make sense? So for instance, if that detection is 1/100, right? So in other words, you can imagine you're watching a centimeter, and you can still resolve 1/100th of a centimeter. That means that any length that drops to be less than 1/100th of a centimeter looks to you like there is nothing there, that it's 0, right? So if this is measuring length, then starting from the 100th row and onwards, the machine will say it's 0. But there is a better machine. A better machine has a better resolution, and that means smaller epsilon. It's able to resolve smaller distances, right? So that machine might be able to resolve within 1,000th, right? So then you go down, and once you reach below 1,000th, the machine is no longer able to detect, right? So the delta epsilon proof, or in this case, n epsilon, the integer epsilon, just says this: any machine that is watching this this sequence, any machine that is looking at this columns, will at some point stop saying anything other than 0. It will eventually, starting from one row and onwards, it will say it's all 0, right? So that's what you say for any, the way you say it mathematically, you say it this way. So you say for, in this context, for any epsilon bigger than 0, there exists, it just means there is some exists, and I call it n epsilon because it's different, right? It's the row at which the machine stops detecting. There exists an entry in the row, I call it n epsilon. For epsilon 1/10, it's different for epsilon equal to 1/100, right? And onwards, right? There exists n epsilon such that the target, let's say a n minus L in this case is 0, is less than epsilon for all n bigger than or equal to n epsilon, right? What is this saying? What is this statement saying in human language? It's just saying the detector, the machine that is trying to tell whether it's L or not, is saying it's not, it's L. It's saying always it's L starting from the row n epsilon, right? That's all it's saying. It's just for this machine, for each machine observing this, for each detector looking at it, there exists a particular entry, right? Beyond which the machine is just saying, yes, it's always the same. It's always L. Make sense? And it's different for different machines, because you can see if I select a different epsilon, that means I select a different detector that's able to resolve to within that epsilon. So some machines will stop detecting from 3rd entry, some machines will stop detecting from 7th, some will stop from detecting from the billionth entry. But all of them eventually, as they look at this thing, they stop detecting. right? So that's a strong convergence. Do you understand why it's called strong convergence? Because all machines stop detecting. Right? There is a point, finite point, beyond which they all stop detecting. That's known as strong convergence. I can erase this, yes? Now, what is weak convergence? Weak convergence, let's look at a different sequence. So let's look at the sequence Bn. Bn is equal to 1 whenever the integer is a power of 2. Okay? It's an integer that is a power of 2. So let's look at entry number 1. So entry number 1, it's well, let's say it's 0. We want it to be positive power 2, right? Not negative, but positive power 2. Let's say, right? So 1 is 0. What about 2? It will say, okay, I detected. 2 is power of 2 to the 1, so it's 1. Then 3 not, then 4 is 1, right? So then 5 is going to be 0. 5 is not an integer power of 2. 6 is 0, 7 is 0, 8 is going to be 1, right? And the next one is going to be 16th, and the next is 32, and so on. And you can see the distance between successive ones is growing. It's becoming larger, essentially twice as large as the previous distance, right? So what will happen if you apply a detector to this machine, right? So the detector, the computer, it looks down. So yes, detected difference. Yes, detected difference, and then it's kind of slow. No, 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 no. Yes. No, 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 yes, right? And eventually, imagine between 2 to the 100th and 2 to the 101th, right? Can you imagine how big is the distance? It's going to be saying no, 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 no. You're going to sleep. It's already, and you wake up and it's still saying no. And months pass by and years, and you're getting old, and this machine is saying no, 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 right? And you're about to die, and it says yes, detected, right? So right before you're about to publish your result, and the machine says yes, there is a difference, it's not 0, and you have a heart attack and you're done for, right? So this is called weak convergence. You understand? Weak convergence means that detection happens, but it happens very infrequently, right? As you go down the column, essentially you will see very, very rare occurrences of that, right? So that's why the language of weak law of large numbers. It's not weak, it's a very nice law, right? And it's not that the strong law of large numbers is giving you necessarily a better interpretation. It just gives you the two things that are saying very, very different statements. The weak law of large numbers is telling you that if you decide to look at a finite table, in other words, you don't go forever, but just decide to look far enough, but not forever, you will eventually be unlikely to detect any difference. Eventually, it will look to you like you reached your target. In other words, for our purpose, if you simulate, if I throw a coin 1,000,000 times, right, it's very unlikely that I will see the average equal to 0.6. Understand? It's going to be very unlikely, and even more unlikely that understand, right? The more if I do it 1,000,000,000 times, it's going to be tremendously unlikely that I'll see 0.6. You can estimate how unlikely. That's not, and this the weak law of large numbers estimates how unlikely it will be to witness an aberration. In other words, most experiments, most of them will confirm the same results. They could be very deviant experiments, but they are going to be tremendously not likely, to the extent that you will not witness them. If you run it, if you have a big enough sample, you might never witness it in the life of the universe, but they exist. Those deviations, in theory, they exist. That's the difference. Yes. You understand why the one law is called weak, the other is strong? Because weak, it's only doing it to a finite extent, and then it's going to detect aberrations in theory, but very rarely. That's why we have this estimate. But the strong law of large numbers tells us that if we actually look at the full sequence in totality, and we repeat the experiments even infinitely many times, each sequence in totality always converges to the same value. So although up to a finite extent it's unpredictable, actually the limit ends up being 0. So they are also talking about different tables. Good. Now, very quickly decide, guys, if you want to be tortured by proof of the strong law of large numbers. Let me just scan it for you. Quickly, I need you to decide if you want me to talk about it, and if not, I move to the next slide. Okay. Talk about it or not? Okay, here we go. All right. Why I'm not surprised? Because of the weak law of large numbers. Right? I'm not surprised because of that. It's very possible that all of you say, please, yes, I want to do it. But I thought that it's very unlikely. All right, good. So then we are going to move to the next chapter. And we are in chapter 5. We still have a lot to go. I'm not sure how much I'll succeed to cover. I'll try to cover all of it if possible. Right. So here is a problem that you might have been facing in the past several months, or maybe not. So imagine you want to go and get a haircut, right? Now, you want to select the right barber, right? Some of those right barbers are not available. Some of them will not work with you anymore. So here we have here is one way to try to understand how to make that selection, guys. Right? So imagine you will be watching under essentially a very big magnification how each barber is cutting a hair, right? One strand of hair, I mean, right? So what you observe is that the barber will cut it from 0 to L, where L is the full length of the hair, and you observe the location where the cut is made. Right? Now, of course, the precise location where the cut is made cannot be observed because of the resolution of the video, because of your eyesight. You can just have an approximate understanding. So here, let's begin by imagining that we have this scenario where I can only tell if the hair was cut within the first half of it, this is close to the root, or between 1/2 and 1, right? So maybe the full hair was plucked out, or maybe the cut was made somewhere in here, in which case I think it's essentially in this interval, either this interval or that interval. And I watched again, I watched 1,000 individual hairs being cut, and then I came up with this distribution. Let's say, right? I see that about 1/2 so about 1/4 of the hairs were cut. About 1/4 of the hairs were cut with what appeared to me near the root, by the root of the hair, right? And 3/4 were cut to half the size, or somewhere more than 1/2 or more, right? Because in this case, let's say I'm not detecting too well. I can only see, is it a first half or is it second half of the hair, right? So 3/4 were cut close to the top part, and the others were cut less, right? And what I do, I create histograms, and those histograms are supposed to be what? They're supposed to those are like small, like skyscrapers in Manhattan. The area of the box is supposed to be the probability, right? So you can see the height of this box is clearly bigger than 1. That's not important, because it's not the height of the box that represents probability, it's the full area. It's the base times the height that represents probability. So I adjust the histogram to be so that the area of each box represents the probability of the haircut being done there. Clear? So this plus that equals to 1. Agreed? Now, this is not good enough. I want to have a better sense of it, right? So next, suppose that you have a better video camera, not the one from the 80s, and you can see, maybe from the 90s, I don't know, right? And you can see that these here, you can now tell 4 locations where the hair might have been cut, right? So it's either cut from the root to 1/4 of the hair, from 1/4 to 2/4, and so on, right? And then imagine that what you see is now, again, you construct blue histograms, and they represent the area of each histogram represents the probability that the hair was cut in this interval. So for instance, you can see that most hairs were cut, more frequently they were cut close to the top, right? So it's like this. Right? And then as you improve your resolution, you imagine cutting these intervals into smaller and smaller pieces, and then you have very thin boxes, very thin histograms, skyscrapers, they are constructed in such a way that the area inside of them represents the probability. Are you with me, guys? So far, good? So by construction, the area is the probability. And then you have this green line is the skyline. Imagine that as you do that, you begin to observe that there is this green line, right? As you continue doing it, you observe that that the histograms, when you prove it, are approaching. They become very thin. It looks like they are stacked below horizontal, below an oblique line, or horizontal oblique line. Yes. So far clear, right? I'm just trying to explain to you the intuition of we're talking about continuous random variables, and what are those? They can be really well understood if you have a sense for what discrete random variables are, right? So how do you approximate continuous random variable with a discrete random variable that can take different values that are slightly different? This is a value, this is next. I mean, there's very slight difference, but it's discrete, right? So that's what we do here. And then those histograms, they converge to this line. So here is what we can define. So the line they converge to appears to be y equals to 2x for this particular procedure, right? If I created an animation, you would see them kind of shrinking, and and you would see that we get this approximation. So then if I want to know what is the probability that x is between A and B, that here is cut between position A and position B, I can then simply integrate from A to B the curve 2x dx. Does it make sense? Why do I integrate it? Because what am I doing? I will remind you in a moment what integrals are. It's nothing more than just summations of rectangles, nothing more. Right, so because here is just take any curve. Let's say this is some curve. This is the curve y equal fx, right? If this curve was constructed out of many small histograms, what does it look like? It looks like just a given location at x. It looks like this. Looks like a very thin rectangle. Could be thinner. I just made it fat, but it could be actually a very, very thin rectangle. Hairline thin, right? And this location is x, and the width is dx, and the height is fx. Right, so the probability of x is about fx dx. You agree? Dx represents the width of the rectangle. F of x represents the height. So again, remember we constructed it to be so. There is nothing mysterious here. We just constructed the histograms to represent probability. So if you have this, it's a Manhattan type of sky. There's no space in Manhattan, so you make very thin skyscrapers. And the skyline is just the tips of the skyscrapers. It's just the tips of those concrete jungle boxes that are thin and long. Good. And then what is this, guys? This, let's say I want to know what's the probability of hitting this area. So this is AB. What I just do, I just sum from A to B. This rectangle sign is just a sum. You understand? And if you realize this intuition, then you just are not afraid of integral anymore. You just realize, oh, what am I doing? I'm just summing. I'm doing exactly the same thing I was doing before. I'm just summing rectangles over an interval. Yes? So there is no fear. Yes? Good. So then, of course, we have the laws of calculus. I hope you remember those, right? You took Calc 1, Calc 2, Calc 3. You know the fundamental theorem of calculus. And if you think deeply enough about it, it's pretty obvious why the antiderivative, I can show you at some point if you want, why the antiderivative is related to it's giving you a shortcut to finding area under the curve. If you can find a suitable antiderivative, you can easily calculate what it is instead of actually adding those rectangles by hand, right? And doing the approximation. So if x, for instance, is between one quarter and 1/2, I mean, if I'm assuming that the hair is distributed from 0 to 1, I normalize the hair to be distributed from 0 to 1, let's say, or something like that. And then the altitude at any x is 2x. So the probability that the hair is cut in position x, which is between 1/4 and 1/2, is the integral from 1/4 to 1/2 of 2x dx. And it ends up being x squared evaluated to 1/2 minus x squared evaluated at 1/4. And I get 3 out of 16. Yes. And then here is the definition, right? So the definition is that x is a number between -infinity and infinity. It is said to be a continuous random variable if there exists what is known as a probability density function f from r to the interval 0 to infinity, such that the probability of x in b is the integral of fx dx over b. In other words, a continuous random variable is one for which we can create the skyline, which is just really lots of very, very thin hair thin. So you see this red line. Imagine it's not a line, but a tremendously thin rectangle. So it's like lots of thin rectangles where it looks to you like they're touching the curve at a point. And this curve, that's the skyline, that's the density function, right? And so what's the probability that that an x is in B, right? So it's the sum of those lines, the sum of the probabilities. That if x here, that's the probability. X here, that's the probability. So it's the sum of all the rectangles, which is the integral. Make sense? So we constructed it to work. So it works just because of that, not because of anything, right? Now, here is what I mean, the problem. What problem did you have getting haircuts in the past? I'm not sure, I mean, if you still have those problems, right? Or you stopped having them by now, but you used to have those problems definitely in 2020, right? How do you get a haircut? Yeah. So the haircut paradox. So a barber whose density function is f of x equal to 2x, where the interval is between 0 and 1, comes to cut your hair. What is the probability that this barber will just pick one hair strand and cut it halfway between the scalp and the tip? In other words, cut it exactly at the position 1/2. What's the probability you will take this hair and exactly get 1/2? What do you think? No, is integration from 0 to 1/2 is that he will cut it from 0 from the root to 1/2. So he has a lot of option. It doesn't have to be precise, you know. But let's say you want him to be surgically precise. What's the probability he would actually make it at the point 1/2? Yes, integration from 1/2 to 1/2, which is very good. You all see that it's 0, guys, right? So it's just 0. Okay, what about exactly at 7/8 from the scalp? I mean, we're assuming 0 is right where the hair follicle, where the hair is meeting your scalp, and the 1 is the very, very tip. So what about 7/8? Same, it's 0, right? But what about any other value? What about some value b? Here is a fixed value b. What about this probability that it will cut, the barber will cut exactly at b? Right, just fix any b. We just had 1/2, we had 7/8. What about b? 0. So explain to me, how is your hair being cut? I mean, right? So we just said that the probability at every position of your hair, wherever he is cutting the hair, it's 0. It's possible, right? So 0 at any position. So how is your hair being cut? Well, that sounds like an optimistic thing to say. There is always a dx, but I'm not sure. Maybe it helps some people. If there's always, it's like, I cannot cut my hair. Like there's a dx. It's okay. That's what I would do. Maybe, so there is always a range. I mean, I'm not sure. It's of course a very deep dispute. Is it even possible? Is there such a thing as a point, or is it some sort of idealization? Right? Is there a point? Can you cut something at a particular location? Right? Well, let's say what I mean by B. Let's say it's difficult to say where he will cut it, but when the barber cuts a hair, let's put it this way: when the barber does cut a hair, maybe you believe that the cut was made precisely in one location. It could be, of course, that you don't believe that it's possible. I mean, the scissors are not ideal, right? They have some thickness even at the sharpest point. So you might say it's not exactly in one point, and you approach it in this way. It's not a terrible approach. But I mean, if you do believe in points, you can say something else, right? You can imagine that maybe there is some sort of sense that you could, in some theory, in mathematics at least, you can define that there is a precise point where the cut was made, right? So the thing is, the way I will interpret it is it's not very surprising that the result is 0, because remember, I mentioned in class before that if something is 0 probability likely, it doesn't mean it doesn't occur. That's another way to say. So Ryder, what you said, that there is always a dx, is not at all bad. It's very reasonable in real life. You cannot really cut at a point, right? You always cut away an interval, right? And that makes it some slim probability, but not 0. So that's one thing to say about it. But imagine I have some sort of laser or some sort of atomic scale, or who knows, right? It's hard to say if it can be applicable to the world we know, but we have a mathematical notion of points, right? We can imagine an interval, and we can imagine mathematically breaking it at a point. Maybe, I mean, so it appears. It's a long discussion. Can it be done or not? But if you believe that you can cut the interval at exactly a point, it's still not a paradox, because it means that something occurs but does not occur frequently. You understand? But that means, remember, if you interpret probability as a running frequency, it's a limit, right? It could be that the barber cuts exactly at location B, but you will never observe the barber cut at the same location again. No matter how many times you try, you will not observe it, or observe it so incredibly rarely that the limit is 0. You understand? The limit is 0. So maybe one time was a success, but out of infinitely many trials, you essentially don't see it, or see it so infrequently that the limit converges to 0, right? So you remember, guys, we defined, if you want to ask a person what is a miracle, or explain to some religious person, somebody is holding a candle and praying, and what is a miracle? Miracles happen every day. Miracles are events that have 0 probability of occurring, right? And everything that happens here has 0 probability of occurring. So we live in a world of miracles, just not the ones you like. All right, good. So that's the idea. That's how I think of it. You see, this is what I explain over here, is that in terms of the frequentist interpretation, the number of reappearances of B will just be, well, essentially it will be 0, right? For such a thing as a hair cutting, it will be 0. You will see it once, but never again, and you will never predict which place will be cut exactly, right? So there is each time an exact place where it's cut, but it's never matching with any repeated experiment, right? Or you can use the other interpretation that Ryder offered, right? And that is that you can never actually isolate a point, but that's a little bit a physicist interpretation. I'm not sure what can or cannot be done. All right, good. On the other hand, for instance, if I want to estimate the probability that something is cut between 1/2 and 1/2 plus 10 to the minus 8, right? That ends up being having a very small but non-zero probability, 10 to the minus 8, right? So between 1/2 and 1/2 plus 10 to the minus 8, if that represents centimeters, or that if that represents, I don't know, maybe 10 to the minus 8 represents 1/100th of a micron, for instance, right? So that is very small. That would look to you like a point. That has a probability. That's not 0. Good. And now a very important question, guys. A girl wants to get a haircut, she can go to one of three barbers, and you're going to be her fashion advisor, right? Each individual strand of the barber, that's how the barbers are advertising their work, right? So this is barber number 1. Then you have in the middle barber number 2 and barber number 3. Okay, so this is a girl. Recommend her which barber should she pick, and what's going to be the appearance of the girl that goes to barber 1, barber 2, and barber 3. What do you think? Yes, of course, that's what we do. We have nothing better to do, so that's what we do. Too bold? Well, not quite bold, you see. What this means, okay, so 1 you say it's short here, 3 is long here, right? And B is weird. Okay, so yeah, so here is this girl, she has fabulous hair. We mask her face to keep her privacy, it's important. So here is the result of barber 1, right? Barber 1 is this new fashion, you know, like blended thing, you know. It's all short. Barber 2, it's like you cannot decide what you want to be, right? You want it very long or you want it very short. In other words, some hairs, about half the hairs will be long and half of them will be short, right? So here's a bunch of them. This is called "Don't Harass Me on the Dangerous Streets of New York" type of haircut. Very useful, I recommend. In 1 year or less, you will see. It's already beginning. Yes, so then you have barber 3. It's kind of, I don't know what it is. I mean, he still failed, but you know, he tried his best. He kept the hair more or less like it was before. Good. Okay. Where are you guys, by the way? How many of you are here? You sleeping? Mm-hmm. Okay. Fine. So what are we going to do next? Next is this question. So suppose that we have, let's call it PDF, incidentally, the format in which I expect my exams to be submitted, right? PDF, single file. But in this case, it is a probability density function. And that is what? So this is given by cx squared, where x is between 0 and 2, and 0 otherwise. In other words, that tells us that this, whatever this random variable is, it takes values between 0 and 2, and everything else it doesn't take, right? And this is the skyscraper line. So first we want to estimate the, here we go. Didn't I say that in the beginning of class? I think on Monday you're getting that with a small Kinder surprise, right? So your exams, I will try to submit them on Monday for you. You will receive them back on Monday, and along with the next surprise. So what do we get? C. We need to estimate it. So we know that the probability has to sum to 1. So 1 is the integral. You see, so integral is summation, right? The integral of this function times dx will equal to 1. So we don't need to go to minus infinity. We just need to integrate from 0 to 2. We factor out a c. We have c over 3x cubed between 0 and 2. And that gives us c equal to 3 over 8. You understand what I did here, guys? Okay, and now we are interested in calculating the probability that x is between 1 and 2. And that's simply the integral from 1 to 2. You just integrate this thing, you get 7/8. Not a problem, correct? Here is another example. The amount of time a computer functions before freezing up is a random variable with probability density function f of x equal to lambda e to the minus x over 100. We will see what this is. It's an exponential random variable. Hopefully we will see those later. But right now, what do we need to know? We want to know the probability that it functions between 50 and 150 hours. Okay. So first we need to figure out what is lambda. So we need to integrate this full thing from 0 to infinity because that's all it takes. And when you do that, you get 1. So when you integrate, what do you get? You get this expression. You all remember antiderivatives, that I'm being loose with them, right? But you know how to take the antiderivative of e to the minus x over 100. It's just the same. It's e to the minus x over 100, but there is a minus, and there must be 100 to cancel the 1 over 100 that drops down due to chain rule. So we have this expression, and then evaluating from 0 to infinity gives us lambda times 100, and that means that lambda is actually 1 over 100. Right? Lambda is 1 over 100. It's a very interesting random variable, very weird. We will hopefully talk about it, right? It's like me, it's memoryless. It can't remember anything. So the probability that x is between 50 and 150 is this integral. And it's equal to this quantity. Just once you evaluate the integral, that's what you get. Good. Now here, cumulative distributions play a major role. The cumulative distribution of a random variable is now going to be rather interesting. So it's defined to be the probability that x is less than or equal to a, and that therefore is the integral from minus infinity to the value a of fx dx. That's described in short as CDF, cumulative distribution function. PDF, probability density function, CDF, cumulative distribution. Good. Now, from the fundamental theorem of calculus, recall that the derivative of the cumulative distribution is the density function. Now, why is that the case? Let me just quickly remind you of the fundamental theorem of calculus. So by definition, if I want to take the derivative of capital FA, it's just FA plus H minus FA divided by H, which I just write as 1 over H multiplied, right? Same thing. That's the definition of the derivative if you remember it. Now, what do you get? This is the area from minus infinity to A plus H minus the area from minus infinity to A. So what do you get? You get the area from A to A plus H. You see that? You get this expression. You agree? Because this is just sum everything all the way to A plus H, subtract from it the sum of everything all the way to A, and you just get this segment. Now, I take multiplied by 1 over H and take limit as H goes to 0. What am I going to get? Look at it carefully, guys. It's a continuous curve. It's not true for non-continuous curves necessarily, but for a continuous curve, look what happens. What is this expression? This is the summation of all rectangles multiplied by whatever base here. But once H is small, do you see that this essentially looks like the same rectangle? You see, I make H smaller, smaller, smaller. You can see that already in here, it looks like a rectangle. Because the function is continuous, if x is going to be close to a, the altitudes f of x are going to be very close to f of a, which is the same as a rectangle. Do you see that all? Right? If h is sufficiently small, I'm not sure how small, but for different continuous functions, it has to be a different scale. But push h to 0, smaller, smaller, smaller. Eventually, all the altitudes are looking like fa. Yes? So this integral, this full area is what? This for h small enough, this does not look like a small enough h, but make it smaller, smaller, smaller. And then what do you see? This full integral is the same as 1 over h times fa times h, because this width is h. The width is h. You see? So when I replace this integral by FAH, I mean to say that because the function is continuous, I see a rectangle, and the area of a rectangle is, I don't need to sum small rectangles. I can just take the full big rectangle. I can say height times width. Yes, so it's height times width, but I divide by the height. That's the ingenious reason, right? So that means if I divide by the height, I just get, divide by the width, I get the height. I divide by the width, I'm sorry for my mistakes, I get the height. Is it clear, guys? And that tells me that the derivative, and make sure that you can intuitively, or just like I wrote here, reestablish this theorem. That tells me that the derivative of the cumulative distribution is the density function. Isn't it nice, right? So like if we did it for chapter 4, I mean, what is the cumulative distribution doing for us? Not much. But here, I know its derivative is the density function. So, for instance, here is an application of that. So suppose that, let's just do one question. I think you are getting tired, maybe 1, 2 questions. We'll see. And then we play what, when, where, don't forget. So here is what we have. X has a PDF given by f of x. And y has, we want to find the PDF of y, where y is equal to twice x. So here is how we can begin. So the cumulative distribution of y, we begin with that, because we know the derivative of that will give us the density for y. The cumulative distribution for y is probability that y is less than or equal to a, which is probability that 2x is less than or equal to a, which is the probability that x is less than or equal to a over 2. And what is that? That is the cumulative for x at a over 2. So you see what I did? I converted the unknown cumulative distribution to the one I already know. And so I take the derivative of this guy with respect to a, I get the density, take the derivative of the x distribution, because I need to get this guy, I need to take the derivative of this guy. And that's the same as taking the derivative of this guy. And that is what? By that theorem that we just established, derivative of outside function is the density of x evaluated at this expression, multiplied by the derivative of the inside, which is by 1/2. So now I was able to use the cumulative distribution to come up with a density function of an entirely new random variable, right? Well, and with that, since you look stressed, with that, we will call it an end of the lesson, and we are going to do a what, when, where question quickly. Get ready.